Hello and welcome to today's lesson on induced potential, which is part of the magnetism and electromagnetism topic in GCSE Separate Science physics. So in today's lesson we're going to look at being able to describe and explain the generator effect. So if we're successful and learn in today's lesson, we should be able to describe what the generator effect is, understand how potential is induced in a conductor, describe how the size of the induced potential can change in a generator, and then finally explain the difference between a generator and a dynamo. So in today's lesson we're going to look at the following parts of the GCSE Separate Science physics specification: induced potential and uses of the generator effect, which is separate science only content. Now previously we'd looked at the idea of the motor effect. Now the motor effect is the process of turning electrical energy into kinetic energy, whilst induction is the process of turning kinetic energy into electrical energy. So induction and the motor effect are caused by the same underlying principle, they just act in opposite directions. Now another name for induction is the generator effect. But what is this effect? Well, the generator effect is how electricity is produced in the modern world in power stations. The generator effect is the induction of a potential difference in a conductor if the conductor changes how many magnetic field lines it cuts through per second. Now if the conductor is part of a complete electrical circuit, the current will flow in the conductor. So the generator effect is the induction of the potential difference in a conductor if the conductor changes how many permanent field lines it cuts through. Now the cutting of field lines can be achieved by moving the permanent magnet or by moving the conductor. They both give the same effect. So if an electrical conductor moves relative to a magnetic field, or if there's a change in the magnetic field around the conductor, a potential difference is induced across the ends of the conductor, and if the conductor is part of a complete circuit, a current is therefore induced. Now cutting field lines means that a conductor is going through the magnetic field lines of the permanent magnet. Now changing how many field lines a conductor cuts through affects the size of your induced potential difference. The greater the change in field lines cut by the conductor, the greater the induced potential difference. Now like we said before, you can move the conductor to induce a potential difference, because this will cause the conductor to change how many magnetic field lines it cuts through. But you could also move the permanent magnet to induce an potential difference, because this will also cause the conductor to change how many magnetic field lines it cuts through. Now as a permanent magnet is normally heavier than a conductor, a current carrying wire, it's rarer to move the permanent magnet in this process. Now to understand how electromagnetic induction works, consider the following. A wire which is made of metal has many free electrons in there, or charge carriers in their structure. Now when the wire is moved, the domains line up and form a magnetic field. Now this electromagnet is then placed in between a permanent magnet. So what this means is that the negatively charged electrons get attracted to the north pole, as shown here. So what happens is the electrons all move towards the north pole, and therefore a current is produced. Now this will cause charge to accumulate at one end, and such like this. So therefore this means that the charged electrons are then attracted to the other side of the wire, that then causes the charge to accumulate at this end. So the flow of electrons back and forth produces an alternating current in the wire. Now this happens throughout the process because the wire is constantly rotating. Now the frequency of the wire spinning is the same as the frequency of alternating current produced in the wire. Now, increasing the frequency of the rotation has two effects on the potential difference induced. Firstly, it will increase the frequency, and it will also increase the magnitude, as there's a greater change in field lines cut. Now, we can also consider this idea of electromagnetic induction by looking at the left-hand rule, because remember, when you have movement in magnetism, you also gain a current. So from looking at the left-hand rule, the current must act in the following ways. So this is still the idea of electromagnetism. The same rules apply for the motor effect and the induction effect. So we're now going to look at how you should structure an explanation for induction in your examination. Between the poles of a permanent magnet there is a magnetic field. Because this is a non-contact force, it is represented by field lines. Now the correct name we give in physics for magnetic field lines is magnetic flux. The more magnetic field lines per area, the stronger the magnetic field. When a conductor containing charge carriers passes through or cuts the field lines, this induces a potential difference in the wire. Now, potential difference is the energy per charge. Basically, in this instance, you're giving the electrons energy. Now, it's the actual changing in the cutting of lines which causes the potential difference, not the presence of the conductor, which is why you need movement of either the permanent magnet or the conductor. Now, when the conductor is part of a circuit, the potential difference causes a current to flow. So the potential difference, okay, will then lead to a current in your particular wire. So let's look at the steps of the induction process. Step 1. When a conductor changes how many field lines of the permanent magnet it cuts, a potential difference is induced across the ends of the conductor, and then when the conductor is part of a circuit, this causes a current. Now, for the AQA examination, each step is 1 mark in an examination answer. Now, please note that the current induced is increased if the wire moves faster, if there's more wire in the field, or there's a stronger magnet being used, as each causes a greater change in the number of field lines cut by the conductor. Now, there are 2 types of devices which can carry out induction. Now, power stations carry out this induction process with generators. Now, a generator is a device used to generate alternating current. Okay, so you've got your generator here. So what you can see is that your coil is being rotated in a magnetic field. The current is then induced in this rotating coil. The slip rings are then connected to the coil, and the brush makes continuous contact between the external circuit and the slip rings, allowing a current to flow in the external circuit. Now, you'll notice that a generator has a very similar design to a motor. It contains a permanent magnet and it contains a conductor. Now, a generator uses the principle of induction to produce a potential difference. Now, this current produced will change direction every half a rotation as the permanent magnet polarization and the conductor alignment switches every half a rotation. So when the generator rotates in a full circle, it will produce an alternating current. Now, the generator also contains slip ring brushes. This ensures a continuous contact between the circuit and the generator, so there's always a complete circuit and current will always flow in this generator. Now, the slip ring brushes are made from graphite. We use graphite because it's a conductor and it's slippery, so it ensures the generator rotates as fast as possible. Please note that a generator does not have any slip ring commutators. Now, another name for a generator is an alternator. This tends to be its name when it's used in America. This is because a generator produces alternating current, so it can also be called an alternator. Now, the second type of device which will carry out in electromagnetic induction is called a dynamo. Now, bikes and small inducers, when they produce a potential difference, tend to use a dynamo. Now, a dynamo is a device used to generate a direct current. Now, dynamos, like the generators, use the induction effect to induce potential difference. Now, dynamos contain split ringed commutators instead of slip ring brushes. Now, like in a motor, the split ring commutator swaps the connection to the circuit every half a rotation. So this ensures the current flow in the same direction. So this means the dynamo produces direct current. So let's compare the generator and the dynamo. Generators generate alternating current, dynamos generate direct current. Generators use a slip ring brush, dynamos use a split ring commutator. In a generator, the connections remain unswapped. In a dynamo, the connections swap every half a rotation. But both induce potential difference via the generator effect via electromagnetic induction. Now, you'll notice we can plot out a potential difference time graph due to a generator. Now, a generator produces alternating current, which you can see because the line is going to positive and is going to negative. Now, changing the frequency of the spin affects the frequency of the potential difference output. If you change the frequency of the spin, the strength of the electromagnet and the length of the conductor in the field, it will affect the amplitude of the output, how high your line is. Now, dynamos produce direct current. You can observe this because there's no value in the negative, it's only in the positive in your graph. Now, changing the frequency of spin, the strength of the permanent magnet and the length of the conductor will affect the amplitude of the output. Now, remember, the slip ring brushes prevent the potential difference from being alternating, which is why you need them. Now, let's just look at these 2 ideas. Induction can be carried out by both generators and dynamos. Generators or alternators produce alternating current by using slip ring brushes to maintain a constant connection with an external circuit. Dynamos produce direct current by using split ring commutators to swap connections with external circuits every half a rotation. Now you'll notice that a generator or dynamo consists of an electromagnet and a permanent magnet, the same setup as a motor. The conductor is moved up and down inside the magnetic field. The current then flows in the conductor. So the change in the magnetic field lines cut by the conductor is directly proportional to the potential difference induced by the generator or dynamo. The stronger the magnetic field, the more current produced. The more wire in the magnetic field, the more current produced. And the faster the conductor moves, the more current produced. Now also, just to note, the direction of the current produced in the conductor is changed by either changing the direction of motion of your conductor or by changing the north and south pole of the permanent magnet. So as a result, either of them could change your direction. So the factors which affect the size of potential difference induced in electromagnetic induction include the length of the wire in the magnetic field, the speed of the wire movement, and the magnetic field strength. The size of the induced potential difference is determined by the change in the magnetic field lines cut by the conductor, and all the factors above affect this. Now, let's look at another idea linked into generators. Now, if you drop a magnet through the air and you drop a magnet through a copper pipe, will the magnets fall at different speeds and why? Well, yes, they will. The magnet falling in the air will fall quite quickly, but the magnet falling through the conductor will fall quite slowly. Now, the magnet that falls through the copper rod, the conductor, takes a significantly longer time to fall. Now, what happens is as the magnet falls through the conductor will actually become an electromagnet, because as the magnet falls through the conductor, the number of field lines being cut through that copper rod changes, so you've induced a current in that copper rod, and therefore what will happen is the conductor will become an electromagnet, and the magnet of the conductor will repel the magnet of the electromagnet. Therefore they repel each other, so it will fall slower. Now, why do the two objects repel? Why do they not attract? Well, to consider this, let's see what happens if they did attract. Well, if attraction occurred between the two of them, well, therefore the magnet falling through the conductor would actually fall faster and faster and faster and faster, because falling faster means there'd be more field lines cut per second, so the current induced in the conductor will be larger, so therefore the attraction between the conductor and the magnet will be larger, so it would accelerate and go faster and faster and faster. It will be a positive feedback, so eventually this process would continue until the magnet had an infinite energy, which is impossible in the universe. So what we say is that the induced potential difference must oppose the change in the magnetic field that created it, otherwise the object would gain infinite energy. This is a fundamental law of physics which we call Lenz's law. So there are two laws of electromagnetic induction. There are Faraday's law, which is the size of the induced potential difference produced in a generator is directly proportional to the change in the number of field lines cut per second by a conductor. And there's a second important law, that the direction of the induced potential difference produced must oppose the change in the magnetic field cut which created the potential difference. So if you create a potential difference and therefore a current by making a magnet fall downwards, you will have a current produced upwards. So it's important to note that you always get a repulsive magnetic field in your conductor that is being produced via electromagnetic conduction. So let's summarize what we've learned in today's lesson. If a conductor moves relative to a magnetic field, or if there's a change in magnetic field around a conductor, a potential difference is induced across the ends of the conductor. If the conductor is part of a complete circuit, a current is induced in the conductor. We call this the generator effect. An induced current generates a magnetic field that opposes the the original change, either the movement of the conductor or the change in the magnetic field. You should be able to recall the factors that affect the size of the induced potential difference or induced current, and recall what affect the direction of the induced potential difference or induced current. And you should be able to apply the principles of the generator effect to many different examples. You should be able to understand the generator effect used in an alternator to generate AC and in a dynamo to generate DC. You should be able to explain how the generator effect is used in an alternator to generate AC and in a dynamo to generate DC, whilst interpreting graphs of potential difference against time. So, if we are successful and have learned in today's lesson, we can describe what the generator effect is, understand how potential is induced in a conductor, describe how the size of induced potential can change in a generator, and we can explain how why there's a difference between the generator and the dynamo. So I hope you've enjoyed today's lesson on induced potential, which is part of the magnetism and electromagnetism topic in GCSE Separate Science Physics. Thank you very much for watching and have a lovely day.